So my name is Yarden, as you can tell from the slide. I'm a senior machine learning scientist at PayPal. But what you can see in the slide is that ever since I was 14 years old, I've played bass guitar. That's my passion. Okay. Yeah, that's me. So you're probably asking yourself, okay, playing bass guitar, great. What does this have to do with anything we're talking about today? Well, in a few minutes, I promise I'm going to tell you what me as a bass player or music in general has anything to do with what we're going to talk about today. And what we'll talk about today is how we got better at catching the bad guys. So catching the bad guys is something many of us are working on. In e-commerce, it might be catching the fake reviewers. In social media, it can be catching bot accounts or click farms, or in transportation, where the scammer takes the ride and the victim gets the bill. Fraud takes many different shapes, and that's why that's part of what makes it a hard problem to solve. We use machine learning tools to spot the few bad actors that are trying to exploit our system. And that's exactly what we've been doing in PayPal. Our goal is to keep your money safe. That's a big responsibility, and we're dealing with a lot of money. To put things in perspective, in 2021, PayPal has processed over $1 trillion. That's a lot of money. So obviously, catching the bad guys is something we work really hard on. And let's just say that if fraud detection was an Olympic sport, we would probably win the gold medal. And that's why if we want to improve, we will have to outperform our existing solutions using the same data we already have. In other words, for us to improve, we have to do better than our current best, which is already pretty good, using the same data. Now that we have our challenge set for us, I'm going to take you on a journey on what our data looks like. The type of data I will focus today on is event-driven data. We've got a lot of different types of events describing our users' behavior on our system. Each type of interaction is logged in its designated table. And what we end up with are lots of massive tables with events stored according to their type. But how can we make sense of all this data into a single useful set of features? How would you approach this problem? Well, we can come up with a few easy to implement methods to extract features, but we can probably do better. What if we could describe our event data automatically? And even better, what if we could use the same set of features to solve multiple machine learning tasks? Catch the frauds, the fake reviewers, the click farms, and the freeloading taxi riders. That's exactly what I'll share with you today. I'll walk you through a practical method for unleashing the potential of event tabular data using deep learning. This method allows us to extract even more insights from our data, and it allows us to do so by creating a general purpose embedding that can be used to solve multiple machine learning problems. We are using this method today in production, generating features for hundreds of millions of users each day, features that are used by over 20 live machine learning models. First, let me tell you what the plan for the rest of the talk is. We will start with discussing what we've been doing so far, how we've been extracting features, and how it limits our ability to analyze the data. Then the main dish. We'll talk about the R method for unsupervised sequence embedding. Finally, I will mention how you can apply this approach in your organization, even if your data looks different. So by the end of this talk, you will know how you can generate powerful embeddings for your machine learning tasks. Before we continue, let me tell you a bit more about myself. My name is Yarden Raiskin, and besides playing bass and other hobbies, I have a background in finance and statistics, and I'm a senior machine learning scientist at PayPal. For the last 4 years at PayPal, I've worked on domains such as web intelligence, NLP, sequence processing, and clustering. I'm a member of PayPal's Global Data Science Group and a part of a team of data scientists, and what's unusual about our team is that we serve other data scientists. We achieve that by building horizontal data science infrastructure and solutions, serving all data science teams in PayPal. Now, let's get started. And where should we begin if not what we've been doing in the past? When we were faced with user data, I'm sure I don't have to tell you, we would go to each table and produce simple features such as counters or TF-IDF features, which is nothing more than a fancier counting system. Those approaches are easy to implement, and honestly, often they work well enough. But those type of features have two hidden catches. First, when we are creating aggregated features, counting the logins, counting the transactions, summing up the transaction amount, often a lot of information about those events end up being discarded, simply because we don't have the right processing tools. In other words, we are throwing away valuable information that could be used to solve the problem. The second catch is that we analyze each table separately. We count the login separately, the transaction separately. This process results in features that are unaware of each other because each is generated independently. These independent features completely miss the complexity and interactions between events. And if those interactions are not reflected in our features, then our models don't stand a chance. They will have built-in blind spots. Now, remember earlier when I showed you a picture of me playing bass and I said it has something to do with what we're doing here? Well, it does, because as a musician, as I look at the process of generating aggregated features, it doesn't make sense because each table is analyzed separately. When you listen to a song, it doesn't make sense to listen to each track separately, right? Let's listen to a few short examples to drive this point home. I'm a bass player, so of course we'll start with the bass and drum part. Okay, that's great, but something is missing. It doesn't sound right. Now let's hear the guitar. And let's hear the same part with the vocals to give away the song.
Do you remember 21st night, September?
We can say that each track on its own is doing their job and they're great, but we don't get the same experience as we would if we just listen to all of the parts playing together. All of the interactions of how the different melodies play off each other, that's all missing. The same goes to the way we generate features. When we only look at a single table at a time, we're missing the interactions between the different tables that we would get from somehow combining the data. If we want to hear the data playing together like a band, what should our new method be able to do? Well, first, we should consider the context or the order and the context of the event. The order of the events is important because events happening in a different order could convey different semantic meaning. We also want context, being aware of neighboring events, past events, etc. Next, we have to consider the timing between events. With timing, our method will be aware of not just what comes next, but when does it come next. The third and key point is fully utilizing metadata features. These features can be the country of the login, the transaction amount, the transaction currency. We would like our method to be able to sequentially process these features and not resort to what we were doing with previous methods, aggregating them, or even worse, discarding perfectly good features just because we don't have the right tools to process them. Okay, so this is what we want to be able to do. Now let's see what our method looks like. So we finally got to the part where I describe our three-step method and the method that lets us hear the band playing together. We'll go over the steps at a high level and then we'll jump into the details. First, we gather the data from all the different tables and data sources so that we have all the events and metadata features that we're interested in. Once we've gathered the data, we then aggregate it per user. The second step is describing the sequential data in numeric terms, and we'll see an example of how that happens later. The third and final step is summarizing the sequential data, and this is done using a recurrent neural network, or RNN, autoencoder. For the sake of this conversation, let's call this the GDS method. What do we get at the end of this process? What we get is a single embedding vector, which is a summary of each user's behavior. These types of features can be very powerful. We are using them to help solve a wide variety of machine learning tasks, as we'll see later. Now that you know the outline of the process, let's walk through it step by step. The first step, gathering the data. We pull all of the events we're interested in along with the metadata. Once the data is gathered, we group the data for each user, organizing it as a sequence of events and metadata. Notice that here we change our perspective from tabular data to a stream of events and features over time. But what is this good for? These events and metadata, when combined, make up the user's behavior on our system. By gathering data from different data sources into a single sequence, a single array of events and metadata features, we allow our embeddings, and thus the downstream models that will later use them, become aware of the complex dependencies and interactions in our data. Now we've constructed sequences of events and metadata, but we can't use this information yet. We have to first convert all the data points to numeric values, and that's what the second step is for. The goal here is to transform and prepare the raw data so that we're only left with numeric values that machine learning architectures can work with. We will get there by matching the right embedding technique to each data point. Now, this can be a little abstract, so let's focus on an example. Let's take a single event in the sequence, and let's say it's a transaction event. How can we numerically describe it? Well, we've got the event itself. It's a record that the transaction happened. So we can't use this data point directly, as it's probably encoded as a string or some event ID. If you want to use this data point, we will have to apply an embedding solution here. Well, there are a few options to choose from, but we chose to use word-to-vec. It's a simple technique and it scales well. Note that we are constructing a vocabulary of events. We implicitly assume that our data displays most of, if not all of the events. Okay, so we've handled the event, but we also got the metadata features. Let's assume that we've got the equivalent US dollar amount, the currency, the receiver ID, that's the party that gets the money, and a timestamp. The transaction amount is a numeric value, so it can be used directly. We can still apply useful transformations such as clipping, log, etc. to help with the training. For the transaction currency, we will need to apply an embedding solution similarly to the event type. The receiver ID is the party that gets the money in the transaction. Embedding here using, let's say, word-to-vec typically doesn't make sense because of the high cardinality of this feature. But what we can do, we can, for example, check if we have seen this receiver ID previously in the sequence. This translates to asking the question, did this user buy from this merchant in the past? Let's say that the case here is no, so we place a 0 and we move on. As for the timestamp, we could take the difference of two consecutive events. This provides our sequence with a time dimension so that it is aware of when things happen. Now, I assure you that this is a very simplistic example. As we all know, real data is much more complicated, and it has so many other types of features that need clever embedding tricks. So with real data, it's harder, sure, but the same idea still holds. And even though it's tricky, applying this systematic approach unlocks the potential of the data in ways that a human looking at it and generating features never could. Now, if we apply these ideas to all elements of the sequence, we will end up with an embedding for the event and the metadata features. We then simply concatenate the event embeddings with its metadata embedding so that we end up with a sequence of numeric vectors. So this is the part where we've been waiting for, because now we are able to embed the sequences of numeric vectors that we generated and create complex behavioral features using an RNN autoencoder. Why do we use RNNs? Well, RNN's architecture are designed to consume and encode sequences of vectors sequentially, and this is exactly what we want here. Why do we use autoencoder? Autoencoder model learns a compact representation of the input. In other words, it learns how to summarize the inputs, which in our case describe the user's behavior. Once the autoencoder is trained, we can use the encoder to generate sequence embedding. Note that here we are using the fact that this is an unsupervised process. Features from unsupervised models can be typically or can be often used to solve various machine learning tasks. In our case, in your case, if you've got the labels and you do want a specific solution, you might not want to look into an autoencoder and instead use a supervised RNN or a transformer-based architecture. Now, remember the song we heard earlier and how listening to the separate tracks is just not the same as listening to the band playing together? Well, extracting aggregated features from each table separately, that's just like listening to only one musical instrument at a time. But after applying our three-step method, we can fully appreciate all parts of the song playing together. So instead of analyzing each table separately, which sounds like separate tracks, our data now displays all of the complex interactions, just like the band playing together.
Do you remember 21st night, September?
Great. So you might be thinking to yourself, okay, you've manipulated some data around and applied an RNN. What's the big deal, right? Well, I can safely say that this process had and still does have a huge impact on our modeling approach. Once we've got this process up and running, it's as if a door was unlocked. We've unleashed insights in our data that were previously hidden. We've created general purpose features that form a summary of user behavior. And we've only had to do this heavy lifting once. Now it's easy for other machine learning models to pick up those features and test them. We've had great success stories of these features being adopted by various machine learning models. Those features are being consumed by over 20 live models. Most of the models that have tested these features ended up adopting them. We see these features have a strong contribution on the model's performance. This is an incremental lift, taking great models and turning them into excellent models. I will not elaborate on what models we use or how we use this feature in our model, but what I can say is that we use it in a variety of problems. For example, stopping all sorts of consumer fraud attacks, catching fraudulent merchants, spotting risky merchants, etc., etc. Needless to say that we've developed, or that we had a lot of implementation challenges. The sheer scale of the big data we had to work with presented the real engineering challenge. We've also faced data science challenges in describing the data numerically, due to the fact that real data is much more complicated than the examples we saw here. But as you can see, the results speak for themselves. I think it's a great approach for unlocking the potential of events like tabular data. I want to address the fact that you can still apply the GDS method even if your data is different from the examples I gave of users and transactions. For example, we can apply this method to application log data. Application logs are similar to our examples if we rethink events as log records. Networking and cyber could also work if we can describe the traffic and interactions as a sequence of events and metadata. Same goes to messaging. Pick your favorite NLP embedding model, and conversations become sequences of embedding vectors. So what do these three use cases have in common? When can we apply this method? We can apply when the following three conditions are met. First, our data consists of events or records that can be thought of as events. Second, the data displays most of the possible events, so we are able to construct event vocabulary, and exceptions are treated as out of vocabulary cases. The third condition is that we're able to aggregate sequences of the events over an aggregation key. In the examples I gave, we aggregated over users, but in general, it can be any entity. It can be a credit card. In log data, it can be a service or application. In networking, it can be the device, etc. And here's the bonus point. If your data is multivariate or has metadata, that's when the GDS method shines, because in that case, it has the potential to uncover insights that were previously hidden. In conclusion, we saw today how we can apply the GDS method to create unsupervised embedding that summarize user behavior. The 3 steps are: first, gather your data, describe all the data points numerically, and summarize the sequence using an RNN autoencoder. Remember that by applying these 3 steps, you will have transformed your event-based tabular data into a single general-purpose embedding that captures the user behavior and uncovering previously hidden insights in your data. In other words, you can fully enjoy and appreciate the band playing together. If you found this talk interesting and you think you've got something to contribute, we are hiring. And if you want to continue this discussion with me, you can find me on LinkedIn. Thank you very much.
Do you remember when it first lies September?
Thank you very much, Yarden. Yeah, we'll follow with a few minutes of Q&A. I must say there are tons of questions that were sent to us during this talk. So it means that the audience is engaged. One thing that we're asked a lot is, why did you use RNNs and not transformers? Can you elaborate on that a bit?
Sure. So the advantage we see for applying RNNs versus transformers is the fact that we are using an unsupervised structure for sequence embedding. So it's different than applying, let's say if we have a label and we want to transform the sequence of events and metadata into a prediction or a classification problem, for example, then it makes sense to use a transformer-based architecture. But since we are looking for generating general-purpose features, it makes sense to use RNNs, and those can be used both for a downstream prediction tasks, but they can also be used for a clustering task. They can be used for other segmentation tasks. And I also must say that we are looking into extending this infrastructure to attention-based or transformer-based architecture. So that's definitely in the pipeline.
Cool. Thank you. Another question is about technical things. So how do you deal with data drift in production?
That's a great question. So the way we generate the features is we always take a current snapshot, and we have some sort of parameters of how we define each sequence. We perform some monitoring on the feature distribution over time, so between different runs, and we monitor that there is no significant drift over time. And we also look at the reconstruction error. So when we use the RNN autoencoder, we feed in input sequence, and we also reconstruct the sequence giving the embedding, and we want to make sure that those are as similar as possible, and we measure that using the reconstruction error. So that's a single number that we can use to make sure that we don't have any weird shift, at least in the underlying input event data distribution.
Thanks, Yarden. Another question that we got is about the embedding that you could generate. So how did you check that the model understood specifically the behavior?
Okay, so evaluating the embeddings is a whole topic. If we limited the question to the behavioral part, that's a question that is hard to answer automatically. Basically, once we've applied certain automatic or numeric evaluation methods, we just we took a look at the embeddings that we got, and we tried to make sense of them by just manually reviewing clusters of embedded users, or let's say users that were acting differently from other users. And we did see that being embedded in a different part in the feature space means that your behavior is different.